Yes. Hello, Robina.
Good evening, sir.
Hey, how are you guys?
We find things in you, sir.
I'm well, thanks. Hey, it's been a while.
Yes, sir.
How was your maths exam?
We're starting on Friday, sir, and we're writing paper two
Oh,
on Monday.
okay.
Yes,
I see. Are you ready?
I think so, sir.
You think so?
Yeah.
That's good. That's good. That's good. All right. Now let's just wait for a few minutes for others to join and then we shall start shortly.
Sir. Sir.
Hello.
Sir.
Yes, Rowena.
So for grade 12, in the topic of acids and bases, is there anything added on?
Acid and bases. What did you just say about that?
Yes.
Yeah, what about acid and bases?
Is there anything that's added on for grade 12?
Yeah, calculating the pH as well as
But sir,
hydrolysis of salts. Okay.
yes, sir, but isn't it taken out of the syllabus?
I don't know. I haven't heard about that. What's taken out?
Calculating pH.
I don't think so. Let me just check. Let's just check here. No, it's not.
Okay, sir.
I see. Determine the approximate pH of salt in hydrolysis. Explain the pH scale. Define the concept of Kw. Compare Ka and Kb values for strong acid and compare strong and weak acids by looking at pH, conductivity, and reaction rate. Excuse me. They do not specifically say. I don't know. I'm so not sure. We'll just do it. If it's not there, it's still fine because it means that you will have extra information.
Okay, sir.
Because they do not really say about calculation. They simply say perform calculations based on titration reactions and motivate the choice of an indicator. And for the choice of an indicator, you definitely need pH. I will find out. It's just that now it's a bit too late to find out, but I will consult with few people. All right, let's give it 4 more minutes. Then at 10 past, we shall start. Ne? Okay. Good evening, guys. Lucanio and Onati. Yeah, guys. Let's just get started. It's already 6:10 now, so I think we shall just proceed. We're gonna have to proceed right away. So I want us to finish. Last time when we met, we were doing acids and bases, and I would like us to finish that tonight by looking at few questions, exam-related questions. And then we're gonna just do exactly that. So there are a couple of questions that I want us to look at, and then with the sole purpose of emphasizing on quite a few things. I was looking at this question 10 and I felt like it is something that is worth discussing. So we're gonna start with this question 10 first, and then we shall see which next that we can discuss. But also, you guys, if you have a particular question that you want us to discuss, feel free to send it through to my WhatsApp number or share it in our WhatsApp group, whichever way, and then we shall see what is going on. So should you have any question that you would like us to discuss, instead of me giving you, you can always send those questions and then we shall have a discussion around. Okay. I am in trouble now. I can't find my... Oh, what happened to this thing? I can't find my stylus. I don't know what I did to it. Oh, there you are. That's you. Okay. So without wasting time, let's just get down to it. So here's the question that I want us to discuss, question 10. And then they are speaking about the ionization of ammonia in water to form a basic solution according to that balanced equation. Okay. So we're looking at that. Ammonia is definitely a weak base. Ammonia, definitely, it is a weak base. So the reason for that is because look at how it ionizes in water. It ionizes partially to form the ions. In fact, instead of even ionizing, what it does is that it forms this ion. How so? Through the process called hydrolysis. And then remember how this is formed. It forms what we call a dative covalent bond, wherein the hydrogen ion from the water get attached to the ammonia. But that is not the point here. The point is that ammonia is a weak acid. It ionizes partially from the definition. And that is the reason. Write down the conjugate acid of ammonia. Remember, we spoke last time. When we want the conjugate acid, we want to find the conjugate acid. What we are indirectly telling you here is that ammonia is a base. Remember, it's only the base that can form a conjugate acid. How so? When the base, in this case, what happens for the base? Remember, we take that, for instance, you've got your ammonia, you've got water, and then forming the ammonium ion and the OH minus. So what has happened here? when the acid, or rather when the base accepts the proton, it forms the conjugate base. So conjugate acid, sorry. So this is your base in this case, which has formed this conjugate acid. And what has happened, look at what has happened. Number of hydrogen atoms, you have added one hydrogen ion to this, and then you have increased the total charge from 0 to +1. So that is how you form your conjugate acid from the base. So you increase the number of hydrogen atoms that were already there by 1. You had 3, now you have 4. And also look at your charge, it has increased from 0 to +1. So the question that says, find the conjugate acid of ammonia, they are telling you that ammonia is a base in this case. So the conjugate acid of this ammonia in our case will be the NH4 plus ion. And they further go on to say, that identify that one substance in this that can behave as an ampholyte in some instances or in some reactions. Water in this particular case, specifically, water is an ampholyte. It can behave as an acid in one reaction and as a base in another reaction. So be careful in this particular case. We have to be very careful. So in this case, water is an ampholyte. However, there was this question that we looked at last time. There was this particular question. I think it was question 2. Was it question 2 or this one here? Yeah, it's question 3 actually. In this question 3, water is not an ampholyte. In this specific question, in question 3 here. So be careful when you choose your ampholyte. In this particular question 3 here, I just want to mention this in passing. Do not memorize the fact that water can be an ampholyte. In this specific reaction or question, water is definitely not an ampholyte. How so? Look at this. Oxalic acid, this is your acid, this is your base, which has formed the conjugate base, and this is your conjugate acid. Sorry. This is the conjugate acid here. And this is the conjugate base. So look at water. Water is a base. In the second reaction, this ion is now an acid. Water is still the base here because it has accepted the proton to form this conjugate acid, and this ion has now formed this conjugate base. So look at what happens. Water is a base in both of these reactions. It is not the level, what we call the ampholyte, specifically in this reaction. But look at this ion in this reaction 1. This ion is an acid, but this same ion in reaction 2, it is now an acid. Therefore, for this specific question, water is not an ampholyte. So to answer this question, it is this ion that is now, excuse me, the ampholyte. So let us be careful about that. But in this case, this was just a generic question in 10,1,7. I hope you guys got that. Now they are saying that Elena adds distilled water to a soil sample and then filters the mixture. The pH of the filtered liquid is then measured. He then gradually adds ammonia solution to this liquid and measures the pH of the solution at regular intervals. The graph alongside shows the results obtained. So look at what has happened. By adding by adding the ammonia. It shows you that if you look at your pH, the initial pH of this filtered mixture was 4. This tells me that this soil was acidic. As a farmer, as an agricultural scientist, it is very important that you do this before you plant whatever, because under different conditions, there are certain things or plants that cannot grow under acidic conditions. And how does that happen? Remember what we call acid rain. If you remember what is known as acid rain. Acid rain is a result of the carbon dioxide concentration in the atmosphere when it reacts with the water droplets. So when it rains, only to find that there is a high concentration of carbon dioxide in water, what happens that by the time this water reaches us, it would have formed this carbonic acid. And as a result, what we call acid rain results, because of the carbon dioxide in the air reacting with the water droplets when it rains. So this is acid rain. As a result, you end up with a soil that has got a low pH, the acidic soil. So before you can even do this, remember, you're gonna have to use the fertilizers to control the pH of your soil. You're gonna need the fertilizers. In fertilizers, there is what they call NPK ratio, depending on what you want to grow, but let us not dwell much on that one. So this tells you the initial pH of the initial pH of your soil was 4. Therefore, the soil sample is acidic. The reason is because the pH of the mixture is less than 7. I don't know if there are any questions so far from your side, guys. No questions. Great. Yeah. Good evening, Tolwana. Right. So this is what we wanted to do here. And then the next thing is calculate the concentration of the hydroxide ions in the reaction mixture after 4 cubic centimeters of ammonia is added. Let's read that again. Calculate the concentration of this after we have added 4 cubic centimeters of the ammonia solution. So how can we answer this question? We can answer this question by looking at your graph 1. Your graph, we look at the final after we have added. This is before, this 4, pH of 4, is before the addition of ammonia. But according to graph, after we have added 4 cubic centimeters of ammonia, the pH has now increased to 6. So we are going to use that pH after addition of 4 cubic centimeters of ammonia. The pH of the mixture is now 6. Excuse me. And remember, okay, so that is what we're looking at. Hey, guys, you are disappearing. What is going on? Okay, but we shall proceed. So remember also that pH, by definition, it is equals to minus the log of the concentration of the hydroxide ions. Be careful there. So you've got 6 here minus the log of the concentration of this. Rowena, I remember your concern about whether do we do the calculations on pH. I am so not sure as yet, but should we not be required to do it, we'll just have to forget about it. But anyway, if you'll have extra information which can assist you going forward with your chemistry. So how do we solve this? Okay, so to solve this, first divide by -1 logarithms in mathematics, log of the concentration of that. And then to find the concentration of this H3O plus, remember there is a base 10 here, or you can just use your calculator, shift log. We call that the anti-log. So shift log with your calculator, shift log, then of -6, the anti-log of -6. Your calculator should give us the answer that says 1 times 10 to the power of -6. This is in moles per cubic decimeter. Please do confirm that with your calculator. Can you guys please confirm that for me? Is that correct, Rowena? Okay, thank you, Tulana. Thanks. But we were not required to do this. We were not required to calculate the concentration of the H3O plus. The question was concentration of the OH minus ions in this solution. Remember then that from the auto-ionization of water, the concentration of the OH minus multiplied by the concentration of the H3O plus will give us 1 times 10 to the power of -14. So in this case, I do not know this, but I do know. And then when we divide both sides by 1 times 10 to the power of -6, we can easily see that this concentration is 1 times 10 to the power of -8 moles per cubic decimeters. Right. I hope you guys are still with me. Any questions so far before we proceed? Any questions so far, Tolwana and Lukhanyo, before we proceed?
So could we use a different method, for example, with the pH of 6 that we have for the acid? Could we use that pH plus POH is equal to 14?
Absolutely. Absolutely. That's an alternative method. Absolutely. You are absolutely right. So since we have the pH, we have a concept called the POH. pH plus POH is equals to, is it 14, Tolana?
Yes, sir.
Yeah, it's 14. So we have this 6. Remember, POH by definition, POH is equals to minus the log of the concentration of OH minus ion. So in your case, this will be minus the log of the concentration of OH minus ions. So you are absolutely right. Then this minus log of OH minus concentration of theirs will be equals to 8, so that at the end of the day, you divide both sides by -1. You have log of this. So you are absolutely right, Tulwana. And then the antilog of this will give us this. Antilog, remember, it's shift log in your calculator, which is exactly 1 times 10 to the power of -8 moles per cubic decimeter. So the two methods are equivalently the same. We still get the same answer. Beautiful contribution there, Tulwana. That's a very beautiful contribution. All right. Any questions? Any further questions? Right, let's look at this next question, 10,3 now. With question 10,3, let us look at what, ooh, my tables are a mess on my table here. Right, the next question, or rather instruction, a laboratory technician wants to determine the concentration of hydrochloric acid sample. He adds 5 cubic centimeter of the hydrochloric acid sample to 495. Listen carefully. He adds 5 cubic centimeter of the hydrochloric acid to 495 cubic centistill water to give the total volume of this acid. So after you've added here, remember, you simply add the 5 and 495 to get that 500 cubic centimeters. Then, during the reaction, 50 cubic centimeter, then you take from this container now, you only use 50 cubic centimeters of that acid. And then it reacts completely with 0.29. Listen to what they're saying. It reacts completely, meaning there won't be a limiting reagent, there won't be an excess reagent. The other statement or the other phrase for reacting completely is neutralization or neutralizes. React completely and neutralize have got a common thing. By that common thing, what is that common thing? There is no excess reagent, no limiting reagent or excess reagent. I hope you guys are with me here. Meaning you are neutralizing this acid. To neutralize means to react completely. I hope you guys are listening. So next time when you come across this, please keep that in mind, that okay, reacting completely means you are neutralizing. Okay, and then you have the balance, calculate the concentration of the hydrochloric acid sample. Calculate the concentration of the hydrochloric acid sample. This is a stoichiometric problem now. Stoichiometry. Remember, in stoichiometry, there are a couple of steps in stoichiometry that we need to consider. And those couple of steps was, let's just revisit them. Stoichiometric calculations. The first things in stoichiometry, you can't do anything without this. Why do we balance the equations? Why do we have to balance the equations? And the answer is we are doing that so that we make sure that the atoms are conserved, meaning if I'm starting with 5 sodium atoms, I must end with 5 sodium atoms. One. Secondly, it's so that we also make sure that the mass of the reactants is equal to the mass of the product. That is called conservation of mass. During the chemical reaction, mass is conserved. When the equation is not balanced, it will appear as though the mass of the mixture is not conserved. The total mass is not conserved. So that is a significance of balancing chemical equations. Secondly, after having balanced the equations, if there is a need to, we must identify the limiting reagent. Very important. If you are not neutralizing, there is going to be a limiting reagent. But in your case, we do not have the limiting reagent. Thirdly, before you can't, you must convert the given data. Convert the given data to moles. And then to do that, it depends on what you are given. The given data could be the mass. To convert the mass to the moles, we use the formula. When you are given the mass, you use the formula N is equals to mass over molar mass. When you are given the concentration, You use the formula number of moles is equals to the volume divided by the molar volume at a given temperature. And when you are given, last but not least, when you are given the, no. This is not true, sorry. C is equals to N over V. And then when you are given the volume of a gas, you use the formula number of moles is equals to the volume divided by the molar volume. So this is what. And then after having done that, then you can identify the limiting reagent. To do that, you're gonna have to compare the stoichiometric ratio to the actual ratio. Identify your limiting reagent. Last but not least, then you use the limiting reagent. To calculate whatever is needed. Whatever is needed to do the calculations. So let us look at your steps. Step number 1, we already have the balance equation. Step number 2, let us now convert the given data. What are we given? We are given the mass of sodium carbonate. We are given the mass of sodium carbonate. How do we convert it from the mass to the number of moles? We said we have to use the formula N is equals to mass over the molar mass. So our mass, remember, is 0.29. Sodium carbonate is Na2CO3. There are 2 sodium atoms, each with a molar mass of 23. There is 1 carbon atom with a molar mass of 12. And there are 3 oxygen atoms with molar mass of 16. I don't know what to get there. Can someone please calculate this molar mass? What is this molar mass? 46 plus 12 plus 48. What do you get? 102.
106, sir.
106. Okay, thank you. And what do we get when you divide here?
So 0.0027.
0.0027. Give me more.
35.
35. Okay, this is moles. We'll round off the final answer. Remember, the more you round off, the further away from the actual answer you get. So avoid doing the rounding off until you reach the last step. Try to write as many decimal digits after a comma as you can. Tolwana.
So would you recommend us keeping the answer in our calculators and then using it as it is instead of rounding off to like 5 or 4 decimal places for accuracy?
Absolutely. 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 Remember, in mathematics, Tolwana, you have what you call standard deviation. Standard deviation. The many times you round off, the bigger the standard deviation. Standard deviation, what is the meaning of standard deviation? By how much are you off to the average value that is acceptable? So when we do what we call linear regression analysis in mathematics, we handle that. And remember, there is what we call the percentage error. Your percentage error must never be more than 10% of the actual value. So after round, the more you round off, and even also the marking people, they will tell you that these are the acceptable values. We accept a minimum value that is this much and the maximum value that is this much. If your calculations is out of that range, then your answer is already wrong. What causes that? It is rounding off before we reach the final answer. So let us be very careful. Ne? Right. So this is what we have there. So now that we have the number of moles, do we have to identify the limiting reagent? No, but we have the balance equation. Sodium carbonate react with hydrochloric acid. to produce a carbonate will always form a carbon dioxide. It will form sodium chloride. It will form carbon dioxide and water. So balancing this, you have 2. That means we're gonna need 2. I think this is now balanced. Let's check. It is balanced, definitely. Yeah, it's balanced. Now let's just look at that. We are looking at the required ratio. At what ratio should I mix sodium carbonate and hydrochloric acid in order for complete reaction? It reacts completely. It reacts completely. In order to neutralize this acid, at what ratio, that is stoichiometry now, the stoichiometric ratio, at what ratio should I mix sodium carbonate? This is a required ratio from the balance equation. Every 1 mole of sodium carbonate is required to neutralize or to react completely with the 2 moles of it. That is a required ratio, or rather what we call stoichiometric ratio. But what have I actually mixed here? I've actually mixed 0.002735 moles of this. I do not know how many moles of this acid am I going to need. And this now is what we call your actual ratio. And then to get to that, we simply do this the same way we teach ratios and rate in grade 10. So the answer will be 2 times 0.002735. And what is that answer?
So 0.005472.
7?
2.
These are the moles of hydrochloric acid. So these are the moles of it. But what was the question? The question was, calculate the concentration of the hydrochloric acid sample. So what sample did we use? Remember, during the reaction, you have only used 50 cubic centimeter. You have prepared 500 a diluted acid of a total volume of 500, but you did not use everything. You have only used 50 cubic centimeters of that which you have prepared. And there is an assumption that we have to make here. And that assumption is that the addition of this sodium carbonate does not change or affect this volume. Otherwise, without that assumption, this calculation will not be correct. So we are assuming that, remember that when you drop something, for example, the ice cube in the glass of water, the level of water will rise. So the assumption here is that this sodium carbonate will not affect this volume, which is 50 cubic centimeters. So for example, when you get inside the bath, the level of the water in that bath rises because of the concept called the density. And by the way, if you want to determine the easy way to determine the volume of something, of a shape, is to do exactly that. Have your what we call measuring cylinder. So you'll be having your measuring cylinder. So to this measuring cylinder, you add a water to a certain level. And then when you drop a stone, let's say you want to determine the volume of a stone. It's not easy to determine the volume of a stone because it's an irregular shape. Unlike a triangular prism or a rectangular prism or a sphere. A stone is just an irregular shape. So when you drop this stone into this, the level of water will rise from this to another. That difference here will be the volume of the stone. That will be the volume of your stone. Number physics. That will be the volume of the stone. So now we can easily calculate the concentration, and we are done. Concentration 0.005472 divided by the volume, which is 50 cubic centimeters. We convert that into cubic decimeters by dividing by 1,000. And what answer do we get today, guys?
So it's 0.11.
11. Okay.
Yes.
And we are done. Any questions so far? And you are done with this question 10. That was that. Okay. I want us to look at one more question, but before we get to that, any questions from your side, Tolwana, Rowena? Okay, excellent. Let's look at the next question. And look at, I'm not sure, I think we did this question 3 last time, did we? Did we do this question 3, guys? I'm not quite sure. Okay. Not quite sure what we did last time. Let me check here. Evening session, acids and bases. This will tell us. Yeah, we did question 3. Yeah, we have done that. We have done this question 3, so we don't have to redo it again. And by the way, I hope you guys saw that we have uploaded our first 2 sessions, which was on chemical equilibrium as well as acids and bases. So should you happen to have missed this, please go to the YouTube. I've sent you the link, and then you'll find that recording. And also this one will be uploaded as long, tomorrow. We are going to upload this one as well. All right, okay. Look at this question 1. This is also another interesting question, this question 1 here. One of the reasons why it's because it speaks about titration. So I want us to look at titration. Right, a nitric acid is an important acid used in industry, and it is also a strong acid. Nitric acid, remember, nitric acid is used in preparation of fertilizers. Fertilizers. That is what they call Ostwald. I think it's like this. Ostwald process. The chemical engineers at Sasol, they do a lot of Ostwald process. Ostwald process is wherein they prepare nitric acid. It has a certain steps that they have to follow. And then this nitric acid will be used in fertilizers. After this, we have this. One of the many applications of industrial uses of nitric acid is preparation of fertilizers. And the most important thing that you get from there is the nitrogen atom. Remember, I spoke earlier on about the NPK ratio. N is nitrogen. What is nitrogen important for? Let us show you before you guys say I'm the one who's making this up. NPK ratio. No, not that. NPK ratio. No, man, what are you doing? Okay, let's look at that. Oops. It's not supposed to be. This thing doesn't want to recognize my handwriting. Dear God. Okay, let's change this. Oh, I see what is happening here. Should just do NPK fertilizer. Hey, so it's nitrogen. The letter stands for. And then what is nitrogen important for? Hey. There's be understanding. If you are look at this bullet number 1. If you are growing leafy, you'd want to use fertilizer that has a higher nitrogen number of to encourage the growth of your leaves. So if you want to plant your spinach, for example, your cabbage, it's a leafy vegetable. Those are leafy vegetables. Your lettuce, those are leafy vegetables. So for the growth of leaves, nitrogen plays a very important role. So you'd want to choose the NPK ratio that has got a higher concentration of your nitrogen, like in this. So it's very important that you understand. If you guys want to grow plants, please do consider that NPK ratio when you buy your fertilizer. Okay? So you consider all of those things. Now let us look at this. Give a reason why nitric acid is classified as the strong acid. Strong acid, they ionize completely. It ionizes completely. Write down the name or formula of the conjugate base. There you go again, of nitric acid. Remember, when they want you to write a conjugate base, they are telling you that nitric acid is an acid. So how will that happen? It is going to lose, to write down this, remember, we reduce the number of hydrogen atoms by 1. So I'm no longer having the hydrogen. And I have to reduce the total charge from 0 to -1. And that is a conjugate base. Right. I hope you guys are still with me. Calculate the pH of 0.3 moles per cubic decimeter of nitric acid solution. So in your question 1,1,3, I'm given the concentration of nitric acid. Now we have to be careful about these things, guys. This one is a monoprotic acid, which is also strong. A strong monoprotic acid, for a strong monoprotic acid, the concentration of this is approximately the same as the concentration of the hydronium ions. But if it was a polyprotic acid, for example, sulfuric acid, H2SO4, then the concentration of these H3O plus ions will be twice the concentration of your acid. Be careful. Be very careful about that. So you are given this concentration. So this will be exactly the same, which is 0.3 moles per cubic decimeter. Excuse me. And then remember that this pH is equals to minus the log of the concentration of the hydronium ions, H3O plus ions. So this is minus the log of 0.3. We are expecting an answer that is less than 7 because nitric acid, the pH must be smaller than 7 because it's an acid. Can you guys give us the answer?
Zero comma 0.5228787.
522.
522, yes, sir. 8,
5228. Oh, sorry, 523. Let's make it 0.523. KPH doesn't have any SI units. Does it make sense? It should make sense. Why? Because when I look at my pH scale, no, it doesn't require it. It starts and ends. So your pH ranges from 0 to 14, sorry, where 7 is neutral. And then going closer to 0, the acid strength increases. The closer your answer is to 0, the stronger your acid. The closer your answer is to 14, the closer the base. So as the pH gets smaller, the strength of the acid gets stronger. pH decreases, the acid is stronger. I hope you are with me there. Right, listen to what now they are saying. A laboratory technician wants to determine the percentage purity. Percentage purity. And remember, your percentage purity can be calculated using the formula, okay? Mass without impurities of the pure substance divided by the sample mass. Your sample has got even the impurities. This sample mass will be given. This mass of a pure something will be calculated. So we shall consider that. Now, what do they say? What is happening here? They are saying that he dissolves 4.5 grams of the sample. There is your sample mass of magnesium oxide in 100. This is supposed to be cubic centimeters. In 100 cubic centimeters of hydrochloric acid with a concentration of 2 moles per cubic decimeter. Calculate the number of moles of the acid that is added. So what do I have? I've got the volume, I've got the concentration. I should be able to easily calculate the number of moles of the added acid. What am I given? The concentration as 2 moles per cubic decimeter. What else am I given? The volume as 100 moles, cubic centimeters, which we convert to cubic decimeters. And then we can easily now calculate the number of moles from the formula C is equals to N over V, where this is 2, this is not known, and this is 0.1. So multiplying both sides by 0.1, we can see that this number of moles of hydrochloric acid are 0.2. This is a straightforward thing. I believe you guys won't have a problem with that. Now, these are the initial number of moles. He then uses the apparatus alongside to titrate the excess hydrochloric acid in the above solution against sodium hydroxide solution. There are 2 things that they are mentioning to you. So it's a 2-step process if you are reading carefully. 1, the laboratory technician dissolve this magnesium oxide in 100 cubic centimeters of hydrochloric acid. Then the remaining acid is now titrated against the sodium hydroxide. So there are 2 things that you are doing here. So be careful. Please stay with me here. In this question, 1,2,2. There are 2 reactions. Reaction number 1 is between magnesium oxide, which is solid, and hydrochloric acid, which is an aqueous solution. To produce, obviously, the product will be magnesium chloride as well as water. I think, yes, and water, but this is not balanced. So there are 2 of those, and then we put 2 there. It looks balanced now. That is reaction number 1. They are telling you that in this reaction, the acid is in excess. So you are not going to use all of these 0.2 moles. These are the initial moles of the acid. But of this 0.2, not everything will be used in reaction number 1. Certain amount of this will remain. And this remaining is the one that is now being titrated against the sodium hydroxide to produce sodium chloride and water. Did they say neutralization? We will find out. We will find out if it is being neutralized. He then used alongside to titrate acid in the above solution with sodium hydroxide solution. Write down the name of the apparatus in the diagram. This is the what we call, I think you guys know, it's burette. So that apparatus is called the burette. It's a glassware. I hope you guys have seen it before, but in case you haven't seen it, let us just show the picture of what a burette looks like. It looks like that. And it's a very expensive, as you can see. It's a very thin glass that looks like that. So these are your burette. They are very expensive, as you can see. 340 to 130, oh, that's a stand. But the burette, very expensive. So be careful how you handle this, because it can easily break. It's a very thin glass. So your burette will look like that. Okay. And then the next part, the second part of this question, deals with this. Right. You've got this. Your choice of indicator is informed by the salt that will be formed, hydrolysis of the salt that is formed. So it will depend on whether you are titrating a strong acid and a strong base, or a weak acid and a strong base, or the weak acid, the weak base and the strong acid. So in your case, both your acid and base are strong acids and bases here that you are looking at. In reaction number 2, hydrochloric acid is a, is a strong acid. This is also a strong base. Therefore, the salt that is formed is neutral. And remember, what did we say? For a neutral salt, there will be no hydrolysis that is going to take place. Neutral means the pH will be approximately 7. So I must choose. This informs me about the choice of my indicator. The indicator that I must choose must have a pH range of an average of 7. So my pH range here must average to 7. This is less than 7, which means it's acidic. The salt must be acidic. But this is around 7. It's approximately 7. So the salt must be neutral. And this is way above 7. That is alkaline. It's basic. Therefore, my indicator here will be B. I don't know if you guys are still with me. Any questions so far? Any questions so far, Tolwana?
No, sir.
Okay, excellent. It's about to indicate the exact endpoint in this titration. Give a reason for the answer. Because titration of a strong acid and a strong base results in a neutral salt. Okay, the reaction or titration reaction of strong acid and strong base will result in a neutral salt. Neutral salt. So a neutral salt will have a pH of approximately 7. Hence, the indicator must have a pH range of approximately, that's it. So we are informed by the strength of the acid and the strength. During the titration, the technician uses distilled water to wash away any sodium hydroxide hydroxide spilled against the side of the Erlenmeyer effect. Give a reason why the addition of distilled water to the Erlenmeyer flask will not influence the result. So the answer is because distilled water is neutral, it does not affect the pH of the mixture. Distilled water is neutral. It will not affect the pH of the mixture. I don't know if you guys are listening. Distilled water is neutral. I want to show you a titration. We are going to do titration just now. When we finish with this, is neutral. And then therefore it does not affect the pH of the mixture. And that is why we use it. And then at the end point, when you see the word end point again, you must know that neutralization has taken place. And neutralization again means the acid will react completely with the base, or the acid is neutralized by the base. So what does he find? He finds that 21 cubic centimeter of sodium hydroxide, this is a standard solution, has neutralized the excess hydrochloric acid. This excess hydrochloric acid is the acid that remained from reaction number 1. So remember, you are starting with 0.2 moles, but not all of this 0.2 moles is reacted with the magnesium oxide. Okay, I need to rearrange my pages. Right. And there again, the term neutralized. And then calculate the number of moles of hydrochloric acid in excess. How do we do that? We are looking at reaction number 2. And what is our reaction number 2? Reaction number 2 is sodium hydroxide solution neutralizes hydrochloric acid solution to produce the salt, which is sodium chloride and water. So what do I see here? What am I given? I'm given the concentration of what? Of sodium hydroxide. I'm given the concentration of this as 0.2 moles per cubic centimeters. And I'm also given the volume of this. And they said it's what? It's 21 cubic centimeters, which is 0.021 cubic decimeters. Is that correct? 1, 2, 3. Yes, it is correct. And then I can calculate the number of moles of sodium hydroxide to start with. Be careful. So I'm looking at the concentration of sodium hydroxide, the volume that is neutralized, as well as the number of moles. So in our case, C is equals to N over V. And then we've got this as 0.2. And we've got this as 0.021. So you multiply both sides by 0.021. 0.021. Can you assist me with your calculator? And these are the moles of sodium hydroxide. So what do I do now? I want to know, according to the stoichiometry of this reaction, the ratio at which this and that must be mixed so that neutralization takes place is 1:1. Where do we get that from? From the balanced equation. So 1 mole of sodium hydroxide will be neutralized by 1 mole of hydrochloric acid and vice versa. So what do I have? I've got 0.0042 moles. How many moles of this are required? Which is what they want. So you have X equals to 0.0042 moles. Now these are the moles of hydrochloric acid. And that is what they wanted you to do. So look at how we do your stoichiometric calculations. Last but not least, assume that only the magnesium oxide in the sample reacted with the acid. They want us to calculate the percentage purity. So how do we do that? We look at the balance equation there. And then what do we need this for? Remember, the balance equation tells you about the reacted moles, not the initial moles, not the excess moles, but it speaks about the reacted moles. Let us repeat that again. Excuse me. Balance equation tells me about the reacted moles. So I'm looking at my hydrochloric acid. And then I'm looking at this reaction. Magnesium chloride as well as water. So we are looking at this reaction, guys. Kule reaction yakho, when you started this reaction, you've got the initial, you had the certain, you started with a certain amount of hydrochloric acid. You started with a certain amount, which we calculated and found that it was 0.2 moles. This is what we started this with. It was 0.2. A certain amount reacted, and then what remained, which is the final number of moles, or rather, the excess number of moles, which is what we have just calculated now. We found that it is 0.0042 moles. So how many moles now have reacted? Because stoichiometry speaks about reacted moles. Reacted moles is a difference between the two. And what is the difference between these two? It is 0.1958. Am I correct?
Yes, sir.
These are the moles that have reacted here. According to the balanced equation, listen carefully. According to the balanced equation, 1 mole of magnesium oxide will react with the 2 moles of hydrochloric acid. But how many moles of hydrochloric acid have actually reacted? it's 0.1958. Stoichiometry has got to do with the reacted moles. 1 mole of magnesium oxide will react with the 2 moles of hydrochloric acid. The rest of it will remain unreacted. So how many moles of this magnesium oxide? The answer is 2x is equals to 1 times 0.1958, and then we divide both sides by 2 to get, what do we get there? 0.0979, is it?
Yes, sir.
So these are the moles. And then from there, remember, the intention is to calculate the percentage purity. And in a percentage purity, we need to find the mass. So the question is indirectly asking us to calculate the mass of magnesium oxide that has reacted. So once I have the number of moles, it should be easy now to calculate the mass of the sum of the pure magnesium oxide. And what is the molar mass of that? For magnesium, it's 24, right? The molar mass of magnesium is 24. That of oxygen is that. This is 40. Am I correct, guys? From the periodic table. And what is this mass equals to? Can you help us with the calculator, guys?
So it's 3,916.
3,916
Yes.
Grams. And once we have done that, we are done. So our percentage purity will be this over the sample mass. Remember, the sample mass was given initially as 4,5 grams. And you have your answer times 100. And what is the percentage purity?
87,02.
Repeat that again.
87,02%.
Excellent. There we go. There we go, guys. There we go. Let's hear some questions from your side. You guys got any questions for me? Any questions, Tolwana, from your side?
No questions then.
Are you happy so far? I want us to look at this titration thing. Action. Okay, let's look at this titration script. So it's a beautiful concept that they have here. Let's just quick start titration level 1. Okay, so here's an instruction. Hello, my name is Dr. Jay Patel. I'm not Dr. Jay Patel, I'm Mr. Sandy Levilane. And I'm an analytical chemist, and I'll be guiding you through the activities in this level. In level 1, you'll analyze samples from a river that has been contaminated with acid. You'll perform titration experiment to work out the concentration of the acid in the samples. In each activity, you'll be able to collect points. At the end of the level, you can restart to improve your skills. Okay. Right. They explain first part is about the video which explains. Okay. But I need you guys to hear the sound. So I need to stop sharing and share again to include the sound. So here is the video. Listen to what they are saying.
Breaking news. There has been an accident involving a lorry carrying over 1,000 litres of hydrochloric acid. It is feared that some of the acid might have leaked into a nearby river upstream of a site of special scientific interest. Chemists are at the scene to assess the damage and work out how acidic the river has become. When an acid, for example hydrochloric acid, is mixed with water, it completely dissociates, producing a solution of hydrogen ions and chloride ions. Acids can be neutralized by substances called bases. Bases that are soluble in water are called alkalis. When an alkali, such as sodium hydroxide, is dissolved in water, it completely dissociates, so that all of the sodium ions and hydroxide ions are dispersed randomly in the solution. An acid and alkali react to form a salt and water. For example, sodium hydroxide and hydrochloric acid react to form sodium chloride and water. If we draw the dissolved compounds as ions, we can simplify the equation leaving out the sodium ions and the chloride ions. They are known as spectator ions because they appear on both sides of the equation. When we have removed all the spectator ions, we are left with the net ionic equation, showing just the hydrogen ion and the hydroxide ion reacting to form a molecule of water. A concentration of a solution tells us the amount of a substance dissolved in a volume. It is measured in moles per cubic decimeter. We can determine the concentration of hydrogen ions in an acid solution by performing a titration experiment. As the acid is added to the alkali, the hydrogen ions react with hydroxide ions to form molecules of water. The end of the titration is when all of the alkali has reacted. At this point, the pH is neutral. We use an indicator compound which changes color when the point of neutralization is reached. In this example, the balanced equation shows that 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. The amount of alkali can be calculated using the known concentration and volume of the alkali solution. The volume of acid that reacted can be read from the burette. It's good practice to repeat the titration and calculate the average volume added. We can now rearrange the equation to calculate the unknown concentration of acid. As part of the environmental response team, you will have to act quickly to assess the environmental impact of the acid spill and advise on an appropriate response to protect the site of special scientific interest. Samples from the contaminated river have been collected and transported back to the laboratory ready for you to test. In this activity, you will learn how to set up and run a titration experiment to calculate the unknown concentrations of acid in the samples collected from the contaminated river. You'll need to carefully add just the right amount of acid to the alkali solution to reach the neutralization point and judge when the indicator color changes.
Okay, so I hope you guys was listening to this case study that we are having. So the truck has accidentally spilled the acid into the river, and now the river is contaminated. So we need to determine the pH of the water, and we need to determine the amount of the base that we need to add in order to neutralize the water. So let us look at the next step then. What is the next step? Thank you. I hope you are watching closely and you now know about acid-base titration. Click finish. So step 1 is done. Step number 2. Okay, next activity now. Next, you will get to test your knowledge of titration by completing the short quiz. Okay, you'll have up to 5 attempts. Each incorrect attempt will be scored by 10. Each will be decrease the score by 10 points. So we look at this. When hydrochloric acid fully dissociate or does not dissociate, it fully dissociate because it's a strong acid. The pH of water is approximately 7, which it means that it is neutral. So this is an activity, guys. When an acid and alkali react to form water and salt, this is called a neutralization reaction. A titration can be used to determine the unknown concentration of the base. And then what do they say? An indicator will help us to find what? The point of neutralization or the end point. So this was the next activity. And then you can check. I'm going to share this link so that you guys can also do these activities. Next activity, and you'll have to look at how acidic oil color in the solution affects its pH. Okay, let's look at that. So what are the pH of sodium hydroxide solution? Because it's a base, it must be somewhere above there. pH of this acid, it must be between 0 and 2. And water is neutral, so the pH will be exactly 7. So that's just your pH scale, your basic understanding. So the next step will be now, oh, sorry. Select, what is this?
Look at the sides where it says select all the compounds.
Oh, thank you. Select compounds that are acidic. We all know them, isn't it? This, that, and that. So these are your acidic compounds. We've already selected them. And then this is correct. The next thing now. Okay. Decide if each of the statements about the indicator is true or false. Use the images flask to help you choose the correct. One, they are saying that which one, the phenolphthalein is not affected by the pH of the solution. Is that true? That's not true because it changes color. If it is not affected, it must maintain its color. Look at this. Color of the colors of phenolphthalein indicator. In an alkaline medium, it is this color. At the end point, it changes, so it is affected. Changes color close to a point of view which shows the end point. That is definitely true. When adding acid to the base, it changes color from colorless to pink. Colorless to pink, that is not true. It changes from this to that. Okay. The next thing now, measuring the mass. In this activity, we'll measure the sodium hydroxide using a torque pen and the Boying balance. You will have unlimited appetite to each. You are now entering the laboratory. So you'll need to consider your local health and safety guidelines. Common examples are safety class, hair tie, bag, and lab coats. So let us go into one to measure 1 gram of this. So here is the weighing pen. And then we must add just before you start adding, look at this. You haven't added anything yet. So you have to tear the mass of this pen. So we tear that so that we are starting from 0, 0. And then we can now add our sodium hydroxide. Let's add liquid by liquid. Let's check this. 0.09. Let's check when we add that. 30 grams. 51 grams. 72. Now let's add liquid by liquid because you're getting close. Let's check that. 82. 83. I think I'm gonna take a chance. 94. 95. 96. 97. 98. 99. And then we have exactly the required amount. And let us check. Well done. Now you've scored. Sodium hydroxide has been transferred into a beaker. If you choose to take a break, next you'll prepare solution of sodium hydroxide. Okay, we need to prepare standard solution of sodium hydroxide. This is the solution of known concentration. You need to choose the appropriate equipment to make up the solution to the exact. That is what the but they will show you this equipment. So firstly, I'm going to first add water here. Okay. So I'm going to add the water here. What are they? Dissolve the sodium hydroxide with distilled water. Transfer it to the volumetric flask, which has already been rinsed with distilled water, and make up the total volume of that. So remember to rinse the beaker. Remember to rinse the beaker so that all of the sodium hydroxide is put into this. This is called the volumetric flask. So let us add the water here. We're first going to dissolve this. Okay, Now we have dissolved that. And then after having dissolved this into 100 cubic centimeter, we are transferring the amount into the volumetric flask. But we must remember to rinse the beaker with water. So we are rinsing our beaker, and then now we are transferring that. So once we have done that, to make sure, look at this, we need to fill it to this mark so that it is exactly 250. So let us use now drop by drop. Let's check if we drop this. Okay, let's see if we add so much. Now let us add fewer drops. Okay, fewer drops so that we do not go above that. And then look at this. This is called the meniscus, the curvature of this water. The bottom of the meniscus must be at the level that is required. And then you shall have slightly more than, but I think that is about fine. Restart. We have added too much water. That is a bit too much. So let us restart this once again. So let us add drop by drop. It looks like. Now I'm gonna be extra careful. And don't think this is what we need to see. The bottom of the meniscus is the one that must be at the level that is required, not the top of the meniscus. Let's add one more drop, one last drop. That's perfect. Now let us check. That's correct. You okay? If you choose to take, no, we don't want to take a break. We just want to finish here. I'll aim to calculate the concentration in moles per cubic decimeters of this in the contaminated river. Let's look at that. So what do they want us to do? The relative atomic mass of sodium from the periodic table, you can get that it is 23. That of oxygen, remember from the periodic table, it is 16. And that of hydrogen, it is 1. Okay, so the total is that one. Then let us check, that is correct. Now they want you to calculate the amount of substance in moles. So remember the formula, it is mass divided by the molar mass. And then let's check, that's correct. So we've got the initial number of moles of our sodium hydroxide as 0.0250. As we proceed. Now they want you to calculate the concentration. Remember, concentration is number of moles, amount of substance in moles, divided by the volume in cubic centimeters, multiplied by that. And then let's check that. That is exactly correct. So now we have to calculate this concentration. And there is your number of moles, volume in cubic centimeters. And the answer is already given out. So you are working this out. Okay, now what do the pipette has already been rinsed with water. Now it needs to be rinsed with solution. Fill the pipette so that it roughly half full. You can do this by holding down this button, then rotate the pipette to ensure that it is. Okay, so let us do that. So they said you must hold it down. Okay. And then you must rotate so that you make sure that you are rinsing everything. And then after, now, now we have rinsed our pipette to make sure that it is not contaminated. And what is next? Now transfer 25 cubic centimeters into the flask and add 2. Okay. Start by filling the pipette with the solution. start by filling this. So here's our pipette, and then let us hold it to the required mark. Okay. There we go. And then we are going to now transfer this. And then we add 2 or 3 drops of the indicator, because indicator is the one that will help us to get, they said 3 drops, and we are done. Okay, let us check. Is that correct? Yes. And this is actually what you're gonna be doing in the laboratory, guys. So look, study carefully your techniques of how to do this. I will share this link with you. Next, you will be testing water samples from sites B and C. You need to prepare the burette with the first sample. Consider, click on the site B to begin. So there is site B. Right, to prepare the burette, you need to rinse it. And then fill it with the sample from the site. Start by rinsing the burette with distilled water. As I said, always make sure that the bottom of the burette is below the eye level. The bottom of the burette is below the eye level. So this helps us to control your eye level, as you can see. So do you want this to read it like that? But what did they say? Always make sure that the top of the is below. And there is your eye level. This is above the eye level. Below eye level, this is what they want. Okay. And then what did they want us to do? We must rinse it with water. Okay. Let us check. Was that correct? Yes, that is right. You need to rinse the burette with some of the sample. Okay. Rinse the burette with some of the sample from that. Okay. Let us use a funnel, and then we transfer. Now we have rinsed. That is correct. Next, fill the burette with the sample. So we have to first close so that it doesn't go out. Now we have closed the burette, and then now we are going to fill it with water, with the sample water. Oh no, wait, what did I do? You need to remove the funnel. Oh, okay. Now to read, adjust the eye level so that it is in line with the level of the solution in the burette. This is the correct position to read the burette accurately. Your eye level must be there, right about the bottom of the meniscus. Okay, let's check that. Good, you are ready to do the titration experiment. Now, what do they want us? Do a trial of the titration to get an idea roughly how much of this has been added. Start by reading the initial volume in the burette and then recording. So look at this, we're reading this. They said all your reading should be entered to 2 decimal places and ending either with a 0 or the 5. So I'm looking at this. This is 10, what? 10,1, 2, 3, 4, 5, 6, 7, 5. So the initial volume. Okay, the initial volume is 10, we said, did we say 65? 75, 5, 6, 7, 5. So this is 10,75. Okay, let us check that. That's correct. Click start to begin to run into the flask. Continue adding the sample until solution will become colorless. Click stop at the end which is permanently. So now we are titrating. We are titrating. We must stop when we reach the end point, wherein the color of the indicator has changed. So let us start. Okay, so look at what happens as we add. You will see the color of the indicator will start to change. As you can see, it is changing. Okay, we haven't added enough. When it has permanently changed slightly more, let us check that. Now it has completely disappeared, as you can see. Okay, let us check that. Perfect, that's right. You have correctly identified the endpoint of titration. And then next, now read the final volume. So our final volume is now what? 25,5,6,7,8,95. 25,95. 25,95. Let us check that. That's correct. So we have to now, the difference between 25,95. Can you guys help me with your calculators? What is the difference between 25,95 and 10,75?
15,2, sir.
15,2. So it must end with a 0. Remember, correct to 2 decimal places. And then let's just check that. That's correct. Next, now we are ready to run this. I have started the experiment by taking the initial reading and adding most of the sample from the burette. Now you need to complete the titration by adding the solution dropwise. So click start to begin. Let us now titrate. First, accurate titration. Let's check that. The same thing that we've done. So we are titrating. There we are almost there. Let's check. Should we add one more drop? One more drop. One more drop. Okay, let's check. Let's show. No, you added too much sample. Try when the color change. Okay, let us redo that. Restart. But we have added too much. We have over titrated. Okay, let's redo this. So this is what will end up happening. You mustn't add extra because that you'll over titrate. Let us keep an eye on the sample and the color change. Okay, that's about fine. Let's check. That's correct. Okay, next. Now read the final value. Our final value reading is 27,6. 27,60. So we mustn't forget about that. Check, that's correct. And then what is that? Can you do the difference again, Rowena?
So it's 15,95.
15,95.
Yes, sir.
Okay, thank you. Let's do one last trial, one more time. So, okay, same thing again. So let us start. That's about fine. Okay, so we are done. The final volume, it's 24.95 in this case, 24.95. And we are done with this titration. And the final volume, can you do the difference one on the difference one more time? 15.95 again, isn't it? Isn't it,
Yes.
Rowena? Ah, that's perfect. So you can see this is exactly the same. So you need to calculate the average volume. Remember not to include the trial. You need to round your answer to 2. Average of the two same numbers will be the same number. So 15.95 plus 15.95 divided by 2, you're still gonna get 15.95. Excuse me. Do a trial. Do a trial first to get an idea of roughly how much solution must be. Start by reading the initial volume. Okay, let's just read the initial volume one more. 8.80 here. And then next, we do the titration, running into that. So let us start one more time. I think that's about fine. Check. No, we haven't added enough. Okay. Okay, let us add. It looks fine to me now. Good. So now read the final volume. It is exactly 41.00. So what is the difference? Can you do the calculation there quickly? Rowena, can you help
33,
us?
sir.
43? No, the difference between these two numbers.
33, sir.
Are you sure? No, that can't be true. 41 minus 8.8.
32.2.
Comma 2. Did you say 32.2, Rowena? Okay.
Yes, sir.
All right. Now we are going to titrate again. Right. Let us do it again. So start. I think that's about fine. Not sure. Let's check. Yes, that's correct. So the final volume now is 41.125, 41.25. Okay, next. And then we have 2. What's the difference there? Can you help us with the difference between the two numbers? Tolwana,
33.2.
say again.
33.2.
Remember to 2 decimal places, it's 33.20. Right, and then we do the second. Okay, let's start. Okay, I think that's about fine. Let's check. Perfect. And then we read the final volume. It is 41,95. 41,95. That's correct. Next, can you do the calculation there, the difference?
It's also 33,20.
Good. And then we calculate the average again. It's gonna be the same thing, 33,20. Right. That's right. You've suspected. If you want more practice, okay, then we are done. Next activity. In this activity, determine the concentration of that. Okay, let's look at that. So, amount of this in moles. So we have already mentioned that you're gonna need the number of moles, amount in moles. N is equals to concentration multiplied by the volume and then divide by that. So that should be the answer. Divide by 1,000. So we are, excuse me, that is about 5. So molar ratio, stoichiometric ratio there, 1:1. Sorry, molar ratio from this 1:1. So when you do the ratios here, you can work it out. It will be the same thing, 0.0025. When you do that, you remember that we were doing the cross multiplication. So you end up with the same thing. Now, what do they want you to do? How to realize, okay? Side C. Now, what do they want us to? Concentration is equals to the number of moles multiplied by the 1,000, divide by the volume. Okay, there is a volume. What? Number of moles divided by the volume. And then let's check the answer. That is correct. So finally, we are now inside C once again. And then let us check that we have done that. The answer is, So let us, concentration can be converted into pH. Use the data from each sample site along with the water quality standard information to answer the true or false question. The pH in the river, pH of the river is normally neutral. That is true because we can see site A is not contaminated. And look at that, pH is 7, that is true. The pH, when the concentration of the acid increases, absolutely true again. pH of the pH decreases because the pH of the acid is less than 7. So when you add acid to a neutral substance, the pH will decrease. pH at the site of special scientific site C is good. Site C, what is the pH at site C? Is 1,1. That is bad. Anything between 0,5 and 4,5 is bad. So this is false. Okay, the pH returns to moderate level by the time it reaches site D. Look at site D, the pH is 4,7. Moderate is anything between 4,6 and 5,9. So this is moderate. That's definitely true. And then, well done. You answered all the questions correctly. Let's see. We are done. So I'm going to share this this link with you, and then you guys can also do your own titration. Practice how to do titration virtually, but in the laboratory, it's a different story altogether. Oh, no. Okay, guys, so that's about it for tonight. We are at 5 to 8, so we are going to end our session right here. I'm not sure if you guys are having any questions. Toluana, any questions from your side?
No, sir.
Rowena? Is Rowena still there?
Yes, sir.
Any questions from your side?
No, sir.
Always, I'm not sure when did you join, so I wouldn't expect you to have seen everything that we're doing. But I'm going to share this so that should you guys be interested in doing this, then you can always revisit this, and then you can always do your own titration experiment. Okay. So as you have seen, there are different levels. The levels will increase. Okay, so you can, where you have made improvements, you can just go to activate, communicate, well done. I've now finished level 1. Let's improve your skills by trying the level again. So you can check your Lendo, your second thing. So you first watch this video like we did before, and then titration of aspirin this time around. Aspirin, yeah. If you do organic chemistry, one of the experiments that you have to do is to prepare aspirin in organic chemistry, practical laboratory. So you look at that when you guys get your own chance. I want to send this link to you. But otherwise, guys, we are done here for this evening. Let us meet again on Wednesday and enjoy the rest of your evening. No, Mr. Makai is not in the office today, so won't be having maths. That will be the end of our session. Hope you guys enjoyed and that you have learned something. Okay. All right. Good night, guys. Good night. Let us rest. Oh, I'm very tired today. Let us rest, and then we shall meet on Wednesday at 8 p.m. Bye. Ooh. Unathi. I didn't see your WhatsApp. Okay, but let's just get this. The link. Let's go. I'm going to